Hey guys! Today we're going to go over problem 523 from the book. This problem says if the roller at A and the pin at B can support a load of up to 4 and 8 kilonewtons respectively, we need to find the maximum intensity of the distributed load so that the supports don't fail. We can start off this problem by making a free body diagram, where if we look at point A, and there's a roller here, we can see that there's only going to be a reaction force perpendicular to that surface contact, which we'll call A over here. Then if we look at point B where there's a pin, we know that there's going to be a reaction force in the Y and the X direction to compensate. We'll call that BY and BX. Then if we get started with our problem, we can start with our equations of equilibrium to find these reactions. I would choose to take the sum of the moments at B, because if we do it at B, then we don't have to take into account BY and BX, and we can just focus on the distributed load and then the reaction force A. So then we could say that 0 equals the distributed load times 4, that's the distance it acts on, times 2, which is the distance between B and then where the middle of the distributed load, which will say that the distributed load will be acting on a point, is 2 meters across, right? Then we can subtract A times sine of 30, which is going to be here, this AX direction, right? And then times 3 sine of 30 degrees, which is the y distance between point A and then B. Then we can also subtract A times cosine of 30, which is going to be A in the y direction, times 4 plus 3 times cosine of 30, which is that original 4 we said the distributed load was acting across, plus the distance between A and this point. So from here to here, that is going to be 4 plus 3 times cosine of 30 degrees. Once we simplify this equation, we'll get A equals to 1.2376 times the distributed load W. Now, in the beginning of the problem, we were told that the support can support a force of up to 4 kilonewtons. So if we know that the force A has to be equal to or less than 4 kilonewtons, then we can figure out that the distributed load can be less than or equal to 3.23 kilonewtons per meter. Then from here, we can move on to the sum of the forces in the x direction, which we only have 2 of. So if we take A in the x direction, we'll have 0 equals A times sine of 30 minus BX. Then since we know what A is equal to, and what W is and all that, then we could find that BX equals to 1.237 W times sine of 30 degrees, which will give us 0.6188 W. Then if we find that the sum of the forces in the y direction, we can find BY. And so here we'll have 0 equals BY plus A times cosine of 30. If you've forgotten, that's the AY we have up here, minus the distributed load times 4, which is the distance it acts on, remember? So that if we simplify this, BY will be equal to 2.9282 W. Then we could find the magnitude of the reaction at B instead of just having BX and BY, which we can take the square root of BX squared plus BY squared, which will give us 2.9929 W. And if we know that this the reaction at B can only support 8 kilonewtons, then we can find that the distributed load has to be less than or equal to 2.673 kilonewtons per meter. I made a little mistake there, so this is less than or equal to. And then that means that because 2.673 kilonewtons per meter is less than the other value we calculated, 3.232, we'll take the smaller one because then if we took the larger one, then the reaction at B would cause the pin to fail, even though A would still be intact. So that leaves us with a maximum distributed load value of 2.673 kilonewtons per meters.